Has this newly discovered planet suddenly disappeared? Located in the constellation of 𝙎𝙥𝙖𝙘, the southern fish, Fomalhaut is one of the brightest stars in the sky. It's a Class A star, therefore is quite hot, and its distance from the Sun accounts for about 25 light years, as measured by the fantastic 𝙎𝙤𝙬𝙬 mission. Fomalhaut is a special star for many reasons. For example, it was used as a stable anchor point for star classification. Its beautiful spectrum has served as a calibration spectrum for all the other stars. It is in fact a Vega-like star surrounded by the circumstellar disk, which results in an infrared excess of radiation. This means that Fomalhaut is quite reddish. Alpha Piscis Austrini, as Fomalhaut is also called, it's not alone. It constitutes a triple star system along with the stars TW Piscis Austrinus and LP 876-10. But what makes Fomalhaut even more special? Keep watching the video to get to know why. You'll also learn that science is not so straightforward and that the same results can lead to different interpretations among the scientific community. In other words, scientists are human and the universe is hard to understand. Basically, in 2008, NASA announced the discovery of an exoplanet. It was November 13th, and Hubble Space Telescope was the author behind this discovery. The historical value of this discovery was quite remarkable, since it was one of the first exoplanets to be directly imaged. In short terms, we had a picture of it. Hubble, the famous exoplanet hunter, and more, was pretty good at its job. In 2005, it resolved the structure of the Fomalhaut star and found that there was a massive cold debris disk surrounding the star. The ring is not centered on the star and has a sharper inner boundary. The presence of this huge disk helped look for exoplanets. In fact, if there was a planet, maybe a massive one with a wide orbit and located in the interior of this debris ring cloud, we would have seen something special. In particular, this planet would have cleared out parent bodies and dust in its vicinity, leaving the ring, appearing to have a sharp inner edge and making it appear offset from the star as we exactly observed. In May of 2008, a planet was identified. Paul Callis and James Graham from NASA found it among images from HST dated 2004 and 2006 in the visible wavelength. NASA released the composite discovery photograph in 2008. Anyway, soon doubts started to arise. In order to understand what was happening, let's clarify how HST's exoplanet detection works. As the name would suggest, direct imaging consists of capturing images of exoplanets directly, which is possible by searching for the light reflected from the planet's atmosphere at infrared wavelengths. The reason for this is because at infrared wavelengths, a star is only likely to be about 1 million times brighter than a planet reflecting light, rather than 1 billion times, which is typically the case at visual wavelengths. One of the most obvious advantages of direct imaging is that it is less prone to false positives, whereas the transit method is prone to false positives in up to 40% of cases involving a single planet system, necessitating follow-up observations. Planets detected using the radial velocity method require confirmation, hence why it is usually paired with the transit method. In contrast, direct imaging allows astronomers to actually see the planets they are searching for. While opportunities for using this method are rare, wherever direct detections can be made, it can provide scientists with valuable information on the planet. For example, by examining the spectra reflected from a planet's atmosphere, astronomers are able to obtain vital information about its composition. This information is intrinsic to exoplanet characterization and determining if it is potentially habitable. In the case of Fomalhaut B, this method allowed astronomers to learn more about the planet's interaction with the star's protoplanetary disk, place constraints on the planet's mass, and confirm the presence of a massive ring system. In the discovery paper of the planet, Callis and collaborators suggested that Fomalhaut B's emission originates from two sources, from circumplanetary dust scattering and from planet thermal emission. Therefore, it should be detectable in space-based infrared data if its mass is between 1 to 3 Jupiter masses. But sensitive infrared Spitzer Space Telescope observations failed to detect Fomalhaut B, implying that Fomalhaut B has less than 1 Jupiter mass. Furthermore, although the planet was thought to be a plausible explanation for Fomalhaut's eccentric debris ring, measurements in the Callis and al. paper hinted that it was moving too fast for this explanation to work. As Callis points out, Fomalhaut's debris ring and our solar system's main Kuiper belt are similar dynamically, despite their different ages. A perhaps important difference is that while the classical Kuiper belt has very low eccentricity, the Fomalhaut debris ring has a significant forced eccentricity of about 0.1. Such results, and especially the ones inferred by ALMA, Atacama Large Millimeter Array, led to skepticism about Fomalhaut B's status as an extrasolar planet. So was HST's detection just a simple mistake? Astronomers started to claim that Fomalhaut could actually be a huge dust cloud. In 2021, a team of astronomers published an article suggesting that there was no Fomalhaut B planet. This study was supported by the observations made with the Spitzer Space Telescope. Closed story, you'll say. But no. A few months later, a third article was published in which, on the basis of the data obtained from the Subaru telescope in Hawaii, the authors reassigned the title of exoplanet to Fomalhaut B. All is well that ends well. Wrong. A fourth study published in 2020, in fact, turns around again, bringing back the hypothesis that Fomalhaut B is not actually a planet but a rather large cloud of expanding particles, maybe the result of a cosmic collision. Our study, analyzing all the Hubble data available in the archive on Fomalhaut, says Andres Gaspar, an astronomer at the University of Arizona Stewart Observatory and first author of the publication, revealed several characteristics that together paint an image according to which the planetary-sized object may never have existed. According to the author, there is no planet there, but rather a mixture of ice and dust made up of particles of about 1 micron in size, roughly 1/50th of the diameter of a human hair, produced by the titanic clash of 2 planetesimals, which according to their estimates, they each measured about 200 kilometers in diameter, nearly half the size of the asteroid Vesta. As of today, we can rely on pretty accurate models for the expanding cloud in the Fomalhaut system. Such models are based on our knowledge of the Kuiper belt in the solar system. Similar to the asteroid belt, the Kuiper belt is a region of leftovers from the solar system's early history. Like the asteroid belt, it has also been shaped by a giant planet, although it is more of a thick disk, like a donut, than a thin belt. The Kuiper belt is truly a frontier in space. It's a place where we're still just beginning to explore and our understanding is still evolving. Talking about this dust cloud, I think it would be really illuminating to take a look at this draft article's abstract dated 2018 and signed by astronomers Lawler, Greenstreet, and Gladman. The planet candidate Fomalhaut B is bright in optical light but undetected in longer wavelengths, requiring a large reflective dust cloud. The most recent observations find an extremely eccentric orbit with an eccentricity of 0.8, indicating that Fomalhaut B cannot be the planet that is constraining the system's eccentric debris ring. An irregular satellite swarm around a super-Earth has been proposed. However, explaining the well-constrained debris ring requires an additional planet on an orbit that crosses that of the putative super-Earth. This paper expands upon a second theory. Fomalhaut B is a transient dust cloud produced by a catastrophic collision between planetesimals in the disk. We perform collisional probability simulations of the Fomalhaut debris disk based on the structure of our Kuiper belt, finding that the catastrophic disruption rate of bodies of about 100 kilometers in diameter in the high eccentricity scattering component is several per decade. This model paints a picture of the Fomalhaut system as having recently, within 10 to 100 million years, experienced a dynamical instability within its planetary system, which scattered a massive number of planetesimals onto large high-eccentricity orbits similar to that of Fomalhaut B. If Fomalhaut B is indeed a dust cloud produced by such a collision, we should soon see another appear, while Fomalhaut B will expand until it is either resolved or becomes too faint to be seen. What the article shows is that there are 2 predictions of our Fomalhaut B as a dust cloud hypothesis. This is the first indication that the Fomalhaut B expansion over the coming decades will eventually permit the object to be resolved by our telescopes so that we can observe it better. The second prediction is that more Fomalhaut B-like dust clouds should be created in the system in the near future. If one of those 2 hypotheses turn to be out-verified, we could finally put a pin in it. We just have to wait and stay curious. That's all for this video. Thanks for watching, everyone. What are your thoughts about Fomalhaut B? Do you think it will turn out to be a dust cloud or a planet? Let us know in the comments below. Be sure to subscribe, and we'll see you next time on the channel.